Hey there. In this video, we're going to talk about contingency tables and probability trees. These are some ways where you can use probability and some tools that will help you compute probabilities. Okay, so we're going to start with contingency tables. And this is an example of a contingency table. So we've got a table here that shows the results of a survey that asked 1,000 adults whether they supported or opposed a special tax on junk food. So for every person, they recorded their gender and their opinion. And this table has accumulated how many people fell into each category. So there were 200 people that were male and supported the tax. There were 30 people who were female and unsure. So every box, every cell in this table is telling you a certain type of person, their gender and also their stance on this issue. Also on the right and on the bottom of the table we have the totals. Okay, so we're going to use this table, this is called a contingency table, to compute some probabilities. So let's look at this one. What's the probability that a randomly selected person opposes the tax? Okay, so that means they're one of these people. Okay, so if they oppose the tax, they are one of these people here. Okay, so what's the probability of being one of these people? Well, being male or female isn't specified, so it's just one of the 600, right? So you're one of 600 people, and how many total people are there? What's the size of our sample space? Well, there's 1,000 total people. So it's 600 out of 1,000 people opposed the tax. So that gives us our probability. Right? Our probability is, if I can get my pen to work, A is 600 over 1,000. Okay, or in other words, 0.60. Okay, let's go to B. The person is unsure about the tax. Okay, well, if you're unsure about the tax, that means you're in this column. So there's 100 people that were unsure about the tax. Okay, so we're looking at this. Well, now we're going to compute the probability of choosing one of these people, where there's 100 of them out of 1,000 people. Well, there we go, 0.1. All right, what about C? Opposes the tax or is unsure. Opposes or is unsure. That means you're in this column or you're in this column. So all of these people count. All right? So we're going to look at all of these people. How many of them are there? Well, there's 600 in this column, 100 in this column, 700 total. 700 over 1,000. The probability is 0.7. Okay. What about the next one? The probability that the person is male. Well, the probability that the person is male means they came from this row. Okay. How many people are in that row? There's 520. Out of how many total people? 1,000. .52 is our probability. Okay, what about the next one? Is male and opposes the tax. Is male and opposes the tax. So not only are they male, not only are they in this row, but they're also in this column, right? So they're actually in the intersection of this row and this column, which means they're right here. They're one of 250 people. Out of how many total people? 1,000. The probability is 0.25. Opposes the tax, actually, and I had a little highlight for that, right? It's just that group right there. So and is going to be the intersection of the row and the column. What about opposes the tax or is male? So opposes or they're male. Instead of being male and opposing, they're opposing or male. Well, if you oppose and are female, then you qualify because you oppose. Or if you're male and you support, you qualify because you're male, right? So you just have to be one or the other, either in the opposed column or the male row. So that's looking at this. Okay, so in F here, we are one of this group of people. Okay, so how many of them are there? Well, you might say, well, there's 600 here in this column, and there's 520 in this row. So there's 1,020. But wait a minute. How can that be? Because there's only 1,000 total people. What did we do wrong? Well, if you think about it, when we counted this column, we counted these people, the 250 here. And when we counted this row, we counted these people. We counted the 250 twice. We counted these people twice, so we overcounted. All right, so we have to be a little bit careful. What you could do is count 600 plus 520 and then subtract off the 250 because you undo the fact that you overcounted. Right, so it's going to be 600 plus 520 minus 250 divided by 1,000. Okay, so that's 1120 minus 250 is was that 770? Oh, over 1,000. Forgot that part. Which is 0.77. Okay. Oh wait, or is it 870? Let's see, 870 plus 250. Yeah. That should be 870. 0.87. Okay. Okay. Notice that this looks very much like the probability rule for OR, right? We could have computed these probabilities individually. You could have computed the probability that the person is opposes the tax, right, which was A, 0.6, plus the probability that the person is male, that's part D, 0.52, and then subtract the probability that they oppose the tax and are male, which is 0.25. And if you do that, you will get 0.87. Okay? All right. And that was the probability rule for OR. If you don't remember that, check the last video. Okay? All right. I just want to jump in here and go over some other problems worded a little bit differently, because these kinds of problems can trip people up. Okay? So let's take a look at these parts G through I. All right? Find the probability that a person is unsure given that he is male. Unsure given that he is male. Given that he is male means we know ahead of time that it's a male. So we know we're only looking at these people. So the total number of people we're dealing with now is 520. Now, among those 520, how many people are unsure? Well, 70 of them. So what's the probability for this one? Well, the probability unsure given male is 70 over 520. Okay, which as a decimal is about 0.1346. Okay. Now, you could have also done this using the probability formula for given, right? Remember, the probability of A given B is the probability of A and B divided by the probability of B. The numerator and denominator will be different here because they will be fractions. They are individual probabilities. But when you simplify this out, you'll get the same answer. So it's a good exercise to do it that way as well and make sure you can get the same answer. All right, that's a very good exercise. Okay, the next one. Find the probability that a female supports the tax. Okay, now this is also a given problem. This is a conditional probability. Okay, can you see what's given here? What's known? We know that she is female. That's what's given. So really, in part H here, we are looking at the probability of supporting given that she's female. Support given that it's a female. Okay. Given isn't written here, but you have to understand that it is there, right? Whatever's being assumed is what's given, all right? So, given that she's female, well, how many females are there? There's 480, right? So out of a total of 480, how many of them support 100? Okay. What is that as a decimal? Well, that is 0.2083 approximately. I've rounded, so I'm going to write approximately. Okay, now part I. I'd like you to try this one. This is another given problem. This is a conditional probability. So figure out what's given in here and then compute that probability. Okay? So go ahead and pause the video and work that one out. Okay, 3, 2, 1. All right, let's see what we got here. Did you see what's given? Well, we know that it's a supporter. That's what's given. That a supporter is male, right? So we're looking at the probability of it being a male, given that he supports the tax, right? Given that he supports, because we know that it's a supporter, so that's what's given, all right? So we're going to look at all the supporters, right? How many of them were there? There were 300. How many of them were male? 200. So the probability is 2/3. Might be nice to leave it as a nice fraction, but if you wanted to write it as a decimal, 0.6667. Okay. So sometimes given is hidden in the words. All right. So, but when you do have a given, what you're doing is you're restricting yourself to just one row or one column and using that total as your denominator. Okay. I'll return you to the other me. All right. Let's move along here. Let's do another example. So a test is developed to help determine whether individuals have a certain disease, which affects 1 in 1,000 people. The test is 99% accurate at correctly diagnosing the disease when the disease is present, and it's 95% accurate at correctly diagnosing the absence of the disease when the disease is absent. Okay, so sounds pretty good, right? Suppose you test positive for the disease. How concerned should you be? Would you be very concerned or only a little bit concerned? Okay, well let's compute this out, all right? So we're going to do that by constructing a contingency table, all right? And so what we're going to do is we're going to base our contingency table on 100,000 individuals, okay? So suppose we have 100,000 individuals, and I'm going to get out of the way here, and we have this information, right? So if we have 100,000 people, and 1 in 1,000 of them are infected with the disease, we can fill in these totals here, okay? So I think I'm going to have to redraw this table over here. Okay, so I've redrawn the table, okay? Pretty sloppily, but there it is. And we have a total of 100,000 people. Only 1 in 1,000 have the disease. So only 100 of them will have the disease, which means that the remaining 99,900 of them do not have the disease. Okay? Now, the test is 99% accurate at correctly diagnosing the disease when it's present. So if you actually have the disease, if we're in this row, the test is 99% accurate at correctly diagnosing it. So of these 100 people, 99 of them will test positive. But one of these people that have the disease will test negative. That's what this 99% accurate part means. Now, the test is 95% accurate at correctly diagnosing the absence of the disease when the disease is absent. So 95% of these people will test negative. Okay, so we've got to compute 95% of that number. Okay, and what I get here is 94905. That's how many people who don't have the disease will correctly test negative. How many people fit here? Well, I can either subtract these numbers or I can compute the remaining 5% of this. Either way, I get 4995. Okay, so let's fill in the bottom part of this table. This one's easy, 494906. And here we have 5094. Okay, so we've got our table. Now, so the question we're after is question 3. All right, that's you tested positive. How concerned should you be? All right, but I want to answer these first 2 questions first. All right, just to kind of get some extra practice here. Okay, so let's work on number 1 here. The likelihood of testing negative even though you have the disease. So you have the disease. What's the likelihood of testing negative? Okay, so this is the same as the conditional probability. The probability of testing negative given that you have the disease. So given that you have the disease, we know we're in this row. Okay. Now, what's the probability of testing negative? Well, there's only 1 person out of 100. Note that this becomes our denominator because we're restricting ourselves to this row. All right, so it's going to be 1 out of 100, or 0.01. The probability of testing negative even though you have the disease. And you probably could have told that from this percentage right up here. Okay. What's the likelihood of testing positive even though you don't have the disease? Okay, well that's the same as the probability of testing positive given that you don't have the disease. So given that you don't have the disease means we're in this row, which means you're one of these 99,900 people. What's the probability of testing positive, right? Well, it's 4995 divided by 99,900. Okay, what's that going to be? Well, that's the 0.05. Okay. Okay, so what is the likelihood of having the disease given that you test positive? Well, given that I test positive means that we are in this column here. The people who test positive are here. What's the probability that you have the disease? Well, that means you're one of these people. So it's 99 divided by 5094. Okay, 99 divided by 5094. What is that? .0194 is what I'm getting. Well, check it out. Look, you tested positive. Look at the likelihood that you actually have the disease. It's really quite small, isn't it? Even though the test seems to be very, very accurate. What made this probability so small? Well, it's the fact that so few people actually have the disease. All right, so even if you do test positive, it's still very unlikely that you're going to have it, right? So this is something that people tend to freak out about in the real world. They tend to misjudge these probabilities, right? So it's something you want to be very cautious about. Okay, so let's go to the next example here. This is about, well, the next topic is probability tree diagrams. Okay, so tree diagrams are really useful for computing probabilities. Okay, so if you have events A or B followed by events C or D, then we can make this tree. See, first A happens or B happens. And then after A or B happen, then either C happens, in which case we have A followed by C, or D happens, in which case we have A followed by D. After B happened, either C happened, we have BC, or D happened, we have BD. So these are the four possibilities at the ends of our branches. How do we compute these probabilities? Well, the probability of a possibility at the end of a branch is the product of the conditional probabilities leading to that point. So if I want to compute the probability of A and C, what I'll do is I'll just multiply the probability of A times the probability of C given A. Notice that this is just the multiplication rule, right? It is exactly the multiplication rule. So we're not really learning anything new here. We're just phrasing it in the form of a picture. Okay? Okay, so let's apply this. So a bag contains 3 red and 3 green marbles. Okay? Let's draw a picture here because we can. All right? So I've got I wish I had a color pen, but I don't. So I've got 5 red, 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 and then 3 greens. Green, green, green. Okay? You draw 2 marbles from the bag. Let's assume the bag is thoroughly shuffled up here, and each marble is just as likely to be drawn as any other marble. What's the probability of drawing a red, then a green? Okay, red, then green. So one way you could set this up is to draw a tree diagram. Okay? Actually, I think I have one on the, well, it doesn't matter. I think I had one on the slide, but let's just draw it. So I could draw red or green. Now, after I draw the first marble, I'm going to draw a second marble because I'm drawing 2. So my second draw, I can draw red or green. Now, if I draw red again, I'm actually getting red, red. If I draw green, I'm getting actually red, green, right? After I draw the green, if I had drawn the green first, I could draw a red, in which case I would have green, red, or I could draw another green, in which case I would have green, green. This is the same thing as saying red, first is red, second is red. First is red and second is green. First is green and second is red, or first is green and second is green. Now what I'm going to do is I'm going to write down the conditional probabilities here. Okay, so what's the probability of drawing a red marble? Well, there were 5 red marbles, a total of 8 marbles, so the probability is 5/8. What's the probability on the first draw of drawing a green? Well, there are 3 green marbles out of a total of 8, so it's 3/8. Notice that these add to 1. These will always add to 1 if you do it right. All right, now let's do this probability. Now remember, this is the conditional probability. If you look back on the picture here, these are conditional probabilities. We've already drawn the first marble. So this is the probability of drawing C given that I've drawn A. All right? So this is going to be the probability of drawing red in the second draw given that I've already drawn red. Well, if I've already drawn red, that means that red's gone. Well, one of the reds is gone. All right? Which means there's only 4 reds remaining. 4 out of 7 possible marbles. And what about this? Here I'm drawing a green next. What's the probability of drawing a green given that the first one was red? Well, there's 3 greens out of 7 possible marbles. Notice again, these add to 1. They will always add to 1. Now, what about this situation? Well, I've drawn the green, so now there's a green marble missing. Now I'm going to see what's the probability of me drawing a red next. Well, there are 5 red marbles out of a total of 7. So it's 5/7. What's the probability of me drawing a green next? Well, there's only 2 greens left out of 7 marbles. So this is 2/7. And again, these add to 1. Just a quick check to make sure we did it right. All right, so now what's the probabilities? If I want to know the probability of drawing red, then green, well, that means I went here and then here. So that's this. How do I compute this probability? I multiply the probabilities along the tree. So the probability of red, then green is 5/8 times 3/7, or 15/56. What's the probability of drawing green, then red? Well, first I drew green, then I drew red. I'm here. Probability of green, then red. Well, that's 3/8 multiplied by 5/7. That's also 15/56. What's the probability of drawing both red? Well, you do this one. You do the next two, okay? And we'll check our work together. Okay, so pause the video. 3, 2, 1. And I'm going to come back because I see there's room for me now. Probability of both reds, okay? So, well, I multiply the probabilities along the branches. 5/8 times 4/7. 20/56. And what about probability of both green? Probability of green, green. Well, that's 3/8 times 2/7. 6/56. All right. So this is just the multiplication rule. It's just making a picture first to help us sort things out. So these probability trees can be just a very useful way to kind of make sense of things. All right. All right. So I think that's it for this video. Yep, that's it. So that's it for the videos on probability. I hope you learned stuff, and I'll catch you in one of the next videos.